The engineering history of aviation is usually preserved in two places. It exists in the physical aluminum of the aircraft on the ramp, and it exists in the archive of blueprints that define its geometry. Lose the aircraft, and the drawings can bring it back. Lose the drawings, and the aircraft itself becomes the blueprint. Lose both, and the machine effectively ceases to exist, turning into a ghost defined only by photographs and memories. This is the boundary condition that defines the Fairey Barracuda. Between 1940 and 1945, British industry built these shoulder-wing torpedo bombers in huge numbers. Depending on how the count is framed, sources typically place total production at a little over 2,500 aircraft, roughly 2,600 across all marks. They became the workhorses of the Fleet Air Arm, operating from carrier decks in both the Atlantic and the Pacific. Each carried a crew of 3, a single Rolls-Royce Merlin engine, and a structural layout built to survive the violent loads of dive bombing and carrier landings. Yet by the end of the 1940s, the type had been erased. Not a single complete airframe was set aside for a museum. Worse, the surviving manufacturing diagrams and jig notes were fragmented, some destroyed, some dispersed, in the post-war contraction of the industry. For decades, the Barracuda remained British naval aviation's missing chapter. Because the instructions were gone, photographs can preserve a silhouette, but they cannot specify station lines, rib contours, or load paths. Without the primary source data, any attempt to rebuild the aircraft is only a surface likeness, a cosmetic model, not a functional machine. To solve this problem, a team of engineers and historians needed an archive you could excavate, a physical airframe preserved well enough to read in 3 dimensions. Not a library copy, but a wreck that had survived impact, and then survived decades of chemistry underground. The candidate for this role was a specific airframe designated Delta Papa 872. This Barracuda Mk II was built in 1943. It was assigned to 769 Naval Air Squadron, a unit tasked with the high-risk business of deck landing training. On August 29, 1944, it took off from a naval air station in Northern Ireland for a transit flight. It never arrived at its destination. The aircraft carried a complex set of aerodynamic controls known as Fairey Youngman flaps. These were large, extendable surfaces mounted below the trailing edge of the wing. They could be set to negative angles for dive bombing or extended to increase lift and control at low speed during carrier takeoffs and landings. They were mechanically intricate, relying on heavy castings and precise linkage geometry. In a standard crash, these complex structures are usually torn apart or twisted beyond recognition. If they are destroyed, the geometry is lost. For Delta Papa 872, the flight ended in a catastrophic loss of control. The aircraft did not glide into a forced landing, it fell out of the sky. The specific sequence of the failure is a matter of reconstruction, but the result was a vertical descent into the landscape of Northern Ireland. The wreckage did not scatter across a hard runway or vanish into the deep ocean. It struck a specific geological feature known as Blackhead Moss. This location was not solid ground, but a deep peat bog, vegetation floating on water and decaying plant matter. In terrain like this, impact behaves less like a rigid collision and more like fluid mechanics. The bog doesn't have to shatter an object to erase it, it can swallow it. The investigation into the Barracuda is therefore a dual operation. It is a forensic inquiry into why a competent crew and a relatively new airframe fell from the sky in 1944. It is also a recovery of data, because with the drawings gone, the wreck itself becomes the blueprint. Delta Papa 872 is the only remaining source for the Barracuda's lost engineering DNA, and every bent spar and corroded rivet has to be read as measurement, not debris. The job is to catalog what survived, translate it back into drawings, and extract the geometry required to build a new airframe from the bones of the old one. The challenge is that this evidence has been locked in anaerobic darkness for 27 years. The chain of events begins with an aerodynamic failure. Approximately 5 miles from its departure airfield, witnesses observed the machine enter a spin. This is a condition where one wing stalls more deeply than the other, causing auto-rotation and a rapid loss of altitude. Recovery requires specific control inputs and sufficient vertical airspace to regain unstalled flight. The Barracuda did not have enough altitude. impact was concentrated on the forward section. This part of the airframe contained the Rolls-Royce Merlin 32 engine, a 12-cylinder power plant producing 1,640 horsepower and a major portion of the aircraft's empty weight. When mass of that density meets solid rock or concrete, kinetic energy is dumped through shattering structure and fragmenting components. The release is instantaneous and it is destructive. However, at Blackhead Moss, the impact problem was already set by peat and water, a medium that would not stop the aircraft like pavement. In that medium, the Barracuda's energy would be managed by penetration and drag, not an abrupt stop. When the Barracuda struck the bog, the surface mat failed immediately. The heavy engine and the forward fuselage acted as a kinetic penetrator. They did not stop abruptly at the surface. They punched through the vegetation and continued downward into the peat. The deceleration was rapid but not instantaneous. The viscous resistance of the bog absorbed the energy over a distance of several feet rather than inches. This is the mechanism of impact compaction. The structural consequences were severe but specific. The forward fuselage was crushed longitudinally, effectively telescoping the cockpit section. The wings were torn from their roots by the drag of the peat. For the 3 crew members, the deceleration was fatal. The forces involved exceeded the limits of human survivability. There is no clear evidence of a post-impact fire. Any brief ignition would likely have been smothered as the fuel system and the hot engine disappeared into the waterlogged peat. This rapid submersion created a unique preservation environment. Oxygen poor below the water table, slowing familiar oxidation without stopping chemistry. In waterlogged peat, corrosion pathways change with acidity and dissolved ions, so the outcome is selective and uneven, astonishing in some places, compromised in others, and always contingent on depth, water chemistry, and the materials involved. This created a stark differential in the wreckage of Delta Papa 872. The heavy nose section, the cockpit, and the engine were driven deep into the anaerobic zone. They were locked in a preservation vault. The rear fuselage and the tail section, being lighter, remained near the surface, or partially exposed above the bog mat. The exposed tail section was subjected to the standard atmospheric cycle. Rain, oxygen, and fluctuating water levels allowed aerobic corrosion to begin immediately. Over time, the aluminum skin of the tail would pit and degrade. The steel fittings would rust. The magnesium components would dissolve completely. But 10 feet down, the forward section emerged surprisingly well preserved in places. Beneath the mud, patches of paint still clung to the cowling, and delicate details survived that would normally have weathered away. The bog acted as a fluid packing material, supporting the crushed structures and limiting further collapse under the weight of the overburden. The crash was a violent termination of the flight, but the geological trap ensured that the evidence remained. The aircraft did not burn, it did not scatter, it was driven into the earth and sealed. The wreckage lay undisturbed in the bog's darkness. The location was known, but the technology to retrieve it without destroying it did not yet exist. The recovery would require more than a map. It would require an engineering solution to reverse the physics of the crash. By 1971, nearly 3 decades after the crash, the site at Blackhead Moss was still holding fast. The location was not a mystery to the local population, but the technical barrier to entry remained high. The peat bog that had swallowed the Fairey Barracuda was still an active geological system. It was waterlogged, unstable, and capable of sinking heavy recovery equipment just as easily as it had swallowed the aircraft. The operation to retrieve Delta Papa 872 was not a salvage hunt. It was a formal recovery mission coordinated by the Fleet Air Arm Museum and the Royal Engineers, with 2 priorities: to recover the remains of the crew killed in 1944, and to lift the airframe before the acidic environment could degrade the structure further. The Royal Engineers deployed heavy plant equipment to the edge of the bog. The primary constraint was the water table. The moment a shovel or a bucket breached the surface mat, the hole wanted to flood with black water. To reach the wreckage, the team had to manage that water relentlessly, cutting drains where they could, pumping and bailing to keep the excavation workable. This was not just digging, it was engineering in a swamp that never stopped trying to close. The excavation revealed the violence of the original impact. The tail section, which had remained near the surface, was corroded and fragmentary. But as the team dug deeper, the conditions changed. 10 feet down, the peat was dense and compacted. Here, the wreckage was not just buried, it was gripped by the earth. The extraction of the fuselage brought a hazard the recovery crews knew well. The peat did not just hold the wreck, it gripped it. Wet, compacted bog can cling to broad metal surfaces with a stubborn suction, and a straight vertical pull risks ripping fragile structure apart. To prevent that, the team worked down in the pit with hand tools, clearing peat from around the engine mounts and cockpit rails, freeing edges and seams before attempting the lift. When the nose section finally broke free, the preservation effect was immediately visible. Beneath the mud, parts of the aluminum still held a clean metallic sheen, and patches of paint survived on the engine cowlings. Inside the cockpit, some instrument faces and markings remained legible, preservation that could not have survived decades in open air. This phase of the operation also concluded the human story of the flight. The remains of the 3 crew members were found within the cockpit section. They were recovered with full military honors. Their removal transformed the site from a war grave into an archaeological site. They were later interred at Faunvale Church of Ireland churchyard, closing a file that had been open for nearly 3 decades. With the crew recovered, the focus shifted to the hardware. The Rolls-Royce Merlin engine was lifted clear, followed by the main fuselage section. The wings, which had been sheared off at the roots, were located and retrieved. The wreckage was loaded onto flatbed trucks for transport. However, the moment the aircraft left the anaerobic protection of the bog, a new clock began to tick. In open air, oxygen and moisture could drive corrosion rapidly through newly exposed joints and interfaces. From that point on, the priority was controlled stabilization, preventing unpredictable drying, managing salts and moisture, and cleaning only as conservation allowed. The recovery was a success, but it arrived as thousands of mudcake pieces with no obvious order. The engineers had raw material, but no certainty they had enough of the ship to make it whole. The restoration of Delta Papa 872 is not a standard repair operation, it is a forensic engineering project. In a typical restoration, a mechanic replaces a damaged part with a new one manufactured to an existing specification. But for the Fairey Barracuda, the specification does not exist. The original factory drawings are lost. The wreckage is not just the object to be fixed, it is the only surviving record of how the machine was built. This creates a paradox. To build a pristine aircraft, the team must use a crushed one as the master template. This process is known as reverse engineering. It is the inversion of the manufacturing cycle. Instead of starting with a blueprint and cutting metal, the engineer starts with the metal and draws the blueprint. The objective is to extract the geometric data from the physical object, digitizing the curves, the rivet patterns, and the material thicknesses into a new set of plans. The primary constraint in this process is the condition of the evidence. The crash at Blackhead Moss subjected the airframe to extreme forces. The nose section was compressed, the longerons were buckled, and the skin was tearing at the rivets. The engineering challenge is to distinguish between the original design curvature of a component and the deformation caused by the impact. If a spar is bent 5 degrees, the engineer must determine if that angle was a deliberate design feature for aerodynamic stability or a result of the collision with the peat. If the judgment is wrong, the new part will be manufactured with a built-in failure mode. The most critical assembly was the Fairey Youngman flap system, not as a concept but as metrology. The team needed its tracks, castings, and linkages as geometry you could read back into drawings because a misalignment of even a fraction of an inch would make the flaps bind or fail under load. With the original casting data gone, the surviving components from Delta Papa 872 became the only reference standard in the world. Here, the unique preservation of the bog proved essential. The Barracuda design utilized a significant amount of magnesium in its control systems and gearbox casings. In a saltwater crash, magnesium acts as a sacrificial anode and dissolves completely within weeks. It turns into a white powder and vanishes. But in the anaerobic peat, the magnesium casting survived intact. This allowed the reverse engineering team to measure the wall thickness and the bolt patterns of components that would have been erased in any other environment. The disassembly of the wreck had to be executed with surgical discipline. The steel bolts that held the aluminum and magnesium parts together were often corroded or seized. The team could not simply cut them out with a torch because the heat would warp the surrounding metal and destroy the geometric data. They had to use chemical penetrance and controlled mechanical force to separate the layers. Every rivet that was drilled out had to be cataloged. Every bracket had to be photographed in situ before removal. The result of this phase was a hangar floor turned into a numbered map of parts and measurements. From the nose section of Delta Papa 872, the team could decode the cockpit geometry, the engine mounts, and the wing roots. But as the parts were cleaned and mapped, a significant operational problem remained. The crash had destroyed the rear fuselage and the tail unit. The reverse engineering process had successfully decoded the front half of the aircraft, but the blueprints for the tail were still missing. To build a complete Barracuda, the team would need more than one wreck. The restoration of a vintage aircraft usually relies on a single, continuous airframe. The serial number on the data plate defines the identity, and the engineer works to preserve the continuity of that specific machine. But for the Fairey Barracuda, this standard approach was impossible. The crash at Blackhead Moss had preserved the nose and the wing roots of Delta Papa 872 in remarkable condition, but the rear fuselage was shattered. The tail section was corroded beyond structural viability. To build a complete aircraft, the project team had to make a fundamental shift in strategy. They could not restore a single survivor. They had to synthesize one. This is the logic of composite restoration. It is a process where the viable sections of multiple wrecks are integrated to form a single, complete geometry. It requires a precise alignment of components that were never manufactured to fit together in the first place. The solution came from additional recovery sites. While Delta Papa 872 supplied much of the forward structure, other Barracudas filled the missing geometry, including an airframe designated Lima Sierra 931, recovered from the rugged ground of the Paps of Jura, which contributed critical rear and tail components. What emerged was a composite airframe built from multiple donors, each selected for what it preserved best. This integration is not a simple welding job. Aircraft are built on jigs that ensure the alignment of the longitudinal axis. If the nose section is twisted by a fraction of a degree relative to the tail, the aircraft will be permanently out of rig. The flight controls will not center, and the aerodynamic loads will be asymmetrical. The team had to build a massive steel jig to hold the disparate sections in rigid alignment. They had to effectively simulate the original factory floor of 1943. The challenge was compounded by the manufacturing variations of the war. These aircraft were built by hand, often by different subcontractors. A bulkhead from a bolt and pawl factory might have a rivet spacing that differs slightly from a Fairey-built component. The restoration team had to measure, adjust, and sometimes fabricate interface brackets to bridge the gap between the two airframes. This method allowed the project to achieve a critical metric. The final assembly of the Barracuda is estimated to contain approximately 70% original material. This is a high threshold for a recovery of this complexity. The majority of the primary structure, the spars, the longerons, and the heavy castings, are the actual metal that flew in the 1940s. The gaps are filled with new aluminum, rolled and formed using the reverse-engineered templates derived from Delta Papa 872. The project, known as Barracuda Live, turned this complexity into a public demonstration. The fuselage was not hidden away in a closed workshop. The assembly process became a live exhibit. The public could watch the slow, deliberate mating of the nose and the tail. They could see the contrast between the dark, stained aluminum of the bog wreck and the corroded, pitted skin of the coastal wreck. The result of this composite build is a machine taking shape in 3 dimensions. It is regaining the mass and presence of the original 14,000-pound bomber. When the rebuild is complete, it will sit on its landing gear, and the wings will fold against the fuselage in the correct carrier stowage configuration. A silhouette that vanished from naval aviation history is being brought back, not by imagination, but by measured metal. However, the value of this composite airframe goes beyond its shape. As the team cleaned the surfaces of Delta Papa 872 to prepare them for integration, they discovered that the peat bog had preserved more than just the metal. It had preserved the human touch of the manufacturing process. The final verification of the Fairey Barracuda project did not come from a recovered logbook or a serial plate. It came from pencil markings on the aircraft itself. As the conservation team washed the mud from interior panels of the nose section, they found handwritten notes, not pilot observations, but production calculations and workshop instructions left by the people who built the machine in 1943. These markings included angles, rivet counts, and assembly cues. In ordinary conditions, such notes are easily lost as surfaces oxidize, corrode, and are cleaned over time. But deep in the bog, enough of the original surface survived for the writing to remain readable, offering the team a direct link back to the factory floor. Once those surfaces met open air, the primary enemy of airframe preservation returned. This is the mechanism of galvanic corrosion. It is the inevitable result of the Barracuda's material composition. The aircraft was constructed primarily from light alloy skin and structure, with steel used in selected fittings and frames, and magnesium used in certain castings and housings. When two dissimilar metals are placed in electrical contact in the presence of an electrolyte, such as moisture in the air, they form a battery. The metal with the more active electrochemical potential becomes the anode and corrodes sacrificially to protect the cathode. In the case of the Barracuda, the magnesium components are highly anodic. In electrical contact with steel or aluminum, magnesium can oxidize rapidly, sacrificing itself and weakening the structural integrity of the joint. In the bog, the absence of oxygen and the specific chemistry of the peat suppress this reaction. On the museum floor, the reaction is active. The conservation team must apply rigorous inhibitors to the magnesium surfaces. They must isolate the steel bolts from the magnesium castings using barrier pastes and specialized washers. The preservation of Delta Papa 872 is not a one-time event. It is a continuous battle against the electrochemical potential of its own materials. This technical discipline is what allows the Barracuda rebuild to move from myth into measurable reality. Built from multiple recovered donors, it will stand as the only full-scale example of its type. It will not be a flying machine. It will be a three-dimensional document, a physical record of geometry, materials, and manufacturing decisions that were once thought lost. The legacy of the project is the method itself. The team demonstrated that a missing aircraft type can be approached again when drawings are incomplete, because wreckage still carries the information that factories once wrote onto paper. Twisted metal is not just debris. In the right hands, it becomes an archive. More than 50 years after its recovery, Delta Papa 872 is no longer a ghost. Its surviving structure and preserved markings continue to serve as the reference standard, the closest thing left to the Barracuda's original engineering record, and the foundation on which a complete museum-scale rebuild can finally be made real.